Welcome to this explainer. Today, we're taking a really fascinating journey into the invisible infrastructure that literally powers our digital world. Think of network routing not just as some abstract code or a bunch of cables, but as a massive, intricate spatial puzzle. It's honestly a lot like navigating the busy streets of a sprawling city. We're going to explore how information actually finds its way through these complex internal mazes to keep large organizations running smoothly.
So ask yourself this: how does data find its way through a massive corporate network? Imagine a single giant organization, let's say a major university or a massive global tech company, as a bustling, completely closed-off city. Millions of data packets are essentially commuters, right? And they need to get from point A to point B instantly without getting lost in the gridlock. How do the traffic cops of this digital city know the absolute best route for every single packet, every single second?
Okay, let's dive into this. Here is our roadmap for today's journey into cloud network fundamentals. 1. Welcome to the autonomous system. 2. Goals of Intra-AS routing. 3. 2 ways to route. 4. Keeping the network updated. And 5. Key pillars of Intra-AS routing. Let's get started. Welcome to the autonomous system.
Well, before we can even begin to understand the traffic flowing through our digital city, we first need to establish the city limits. We have to clearly define the domain we're talking about. So, an autonomous system, or AS, is essentially a collection of IP networks and routers entirely under the control of a single organization. It is one unified, bordered territory. The really key takeaway here is that an autonomous system presents a common, unified routing policy to the outside internet. Everything that happens strictly inside these borders is called Intra-AS routing, or Interior Gateway Protocol Routing, IGP for short. It's basically a private, highly managed transit system functioning entirely within the organization's walls, safely insulated from all the chaos of the public internet outside.
Section 2. Goals of Intra-AS Routing.
So how do those traffic cops, our network routers, actually figure out the best routes? Now that we know our city limits, let's look at the mechanics. The primary goal of Intra-AS routing is always to determine the absolute fastest, most reliable path to reach destinations within that same autonomous system. Step 1. The router evaluates metrics. It looks at the cost of a link, meaning, is this path a high-speed fiber optic highway where data can fly at the speed of light, or is it a slower, older copper dirt road? It checks for current congestion to avoid digital traffic jams, and it strictly follows specific administrative preferences. For instance, maybe the IT teams set a policy saying all financial data absolutely must flow through a specific secure firewall. Based on all those evaluated factors, Step 2 is determining the single absolute best path. And finally, Step 3, the router uses this calculated metric to populate its routing table. Every single router within the AS maintains one of these tables. You can think of it as their personalized master map, providing precise turn-by-turn instructions to reach every single possible destination within the organization.
Section 3. 2 ways to route.
When it comes to populating those critical routing tables we just talked about, there are really two distinct philosophies, or rulebooks, used by our interior gateway protocols. First, we have link state protocols, like OSPF, which stands for Open Shortest Path First. Think of this as the meticulous map maker approach, or having a highly advanced bird's-eye GPS system. Under a link state protocol, every single router maintains a comprehensive view of the network's entire topology. They build a complete link state database, meaning they know exactly how the entire digital city is laid out, down to every intersection and every possible detour. On the flip side, we have distance vector protocols, like RIP, Routing Information Protocol. This is a totally different concept. It's kind of like driving without a map and just rolling down your window to ask the person at the next intersection for directions. Instead of a full map, distance vector protocols use metrics like hop counts, literally just counting how many routers a packet has to jump through to reach its destination. They operate by periodically exchanging their routing tables with their immediate neighbors to constantly update their knowledge of what's nearby. It's a super practical step-by-step approach. Two very different strategies for sure, but both achieving the exact same vital goal of keeping data moving forward.
Section 4. Keeping the network updated. Now, our metaphorical digital city is never ever static. So what happens in real time when there's a sudden traffic jam or a major road closure? Say a severed fiber cable gets cut by a construction crew, or a network switch just flat out fails deep in a server room. The answer is fast convergence. This is an absolutely crucial concept to grasp. Routers don't just build a map once, print it out, and forget about it.
They are in constant communication, periodically exchanging routing information to ensure their knowledge of the network topology is completely up to date, allowing for dynamic, real-time adaptation. Fast convergence means that when a network failure occurs or link conditions drastically change, these intra-AS routing protocols are specifically designed to adapt incredibly quickly. They recalculate the math and update their routes in a matter of milliseconds. I mean, they instantly find the detours so rapidly that data just keeps flowing, video calls stay connected, and critical services keep running smoothly without the user ever even realizing something broke behind the scenes. It's basically magic.
Section 5. Key pillars of Intra-AS routing.
Let's zoom back out for a second and look at the foundational rules that keep this entire internal routing system alive. So the crucial point is that to successfully and reliably exchange data within massive organizations, these protocols must rest on 4 key pillars. First up, scalability. These protocols need to be incredibly efficient, capable of handling sprawling digital metropolises, not just small towns, and they have to do it without getting bogged down by endless routing calculations. Second, adaptability. As we just discussed with fast convergence, they absolutely must rapidly respond to real-world chaos, instantly finding detours around roadblocks, link failures, or seamlessly integrating new routers as the company grows. Number 3, compatibility. All the different router traffic cops within that same autonomous system must speak the exact same language. They all need to support the same IGP protocol for effective, seamless communication. And finally, security. Protecting this invisible infrastructure from malicious rerouting or fake traffic signs is totally vital to prevent unauthorized changes and keep the organization's private data entirely secure. So we've seen just how much coordinated effort, meticulous mapping, and rapid adaptation is required just to manage the data traffic efficiently inside one single organization's borders, which leads us to a massive, mind-boggling question to leave you with today. If routing data within a single, highly controlled autonomous system is this incredibly complex, how on earth does data navigate the wild, decentralized chaos between millions of different autonomous systems across the entire globe? Keep that in mind next time you load a web page. Thanks so much for joining me on this explainer, and stay curious.